In this session, I'll be talking about the multiple regression models where our intention is to use more than one predictor, right? In simple regression, we were using just one predictor variable to predict a dependent variable. Whereas here, we would be using multiple predictor variables. So, which means we are talking about multiple drivers which will influence the dependent variable. So, this is where we'll use a similar data which we have used for simple linear regression itself, where I was looking at the overall satisfaction at an amusement park. There we have taken the overall satisfaction and the relationship it carried with respect to the games. Now, what we can very well do is, instead of just this part, we will add a few more variables to the top of it. So that is where we can try understanding the entire multiple regression. So we'll start off with the model. What is the mechanism we have if I have to compare the multiple models? How do I use the model to make futuristic predictions? What do I mean by the standardizing of the predictors? In some cases, I may not take the predictors in their original form. I may do some kind of standardizations or normalizations of the procedure of the various predictors. So what do I mean by that, and why do I really do that? And in some cases, I may have some factor variables as the predictors, like gender, male and female, having a factor variable as a predictor. If that's the case, what is that we are typically going to do? And in some cases, we can have interaction terms. So when I'm using interaction terms, let's say gender alone might influence my dependent variable. Along with that, let's say marital status alone can influence the dependent variable. But at the same time, the interaction between gender and marital status, which means married males versus married females, or married male versus unmarried females. So this is these kind of interactions that when we are building in terms of understanding the relationship to the dependent variable, then we have to talk about the interaction terms. So we would be bringing that aspect as well. And how do I really take care of interactions when I am bringing in the formulas in the multiple regression exercise? What do I mean by overfitting? Right, when I'm trying to fit a multiple linear regression model, in that context, what do I really mean by overfitting, and how do I really overcome the problem of overfitting? And towards the end, I would quickly like to summarize all these steps in one single slide, where if I really want to come out with fitting a model from the data which can be used for predicting purposes, then what is the procedure or what are the series of steps that I typically can get into to do the linear modeling exercise. So let's get started, right? So initially we can go ahead with our original data set itself. We have already seen earlier LM is an R function which takes all your predictor variables that will influence the dependent variable, and it gives me the overall model. So we can use the same LM function which we have used earlier for the simple linear regression model. I can very well use them even in the case of multiple linear regression also. So for that I am getting my data, the survey data, right? Read.csv, I am pulling it from the location where it is there on my system. So just to quickly check, I can do a structure of my survey to recollect what each of the things had. So it's a data frame, 500 observations, 8 variables, weekend, whether the people have visited the park on a weekend, yes or no. So that is what is a factor variable. Number of children with whom they have visited. So in some cases 0, 1, 2, 3, 5. The distance they have traveled to visit that park. It's a numerical variable. The satisfaction they carry with respect to the rides. It's an integer. Satisfaction they are carrying with the games. Again an integer. Their satisfaction levels with the waiting times is an integer. Their satisfaction regarding the cleanliness of the park, again an integer. And overall satisfaction, again an integer. So I would like to model, to start with, I would like to create a model between overall satisfaction and taking these 4 different kinds of satisfaction. So I would like to understand to what extent the satisfaction regarding these 4 aspects are getting reflected as a part of the overall satisfaction of the customers, of the visitors. Now this is where I'll use my linear regression modeling, and because there are multiple predictor variables, I'm taking it as a multiple linear regression model. So I'm storing it as a part of model 2. Right, model 1 I could take it out, probably let's call it as model 1 itself. So wherein I am taking it as an LM function, which is a linear regression model function. So my dependent variable is the overall satisfaction, and I'll take more than one independent variable. And when I am taking more than one independent variables independently, I will keep all of them with a plus sign. So this is what is the relation which I wanted to build, and the data for this that I am taking is my survey data. So this is how the whole linear regression model is created. Now we have the linear regression model in place. So I can very well look at the summary of this model. So I'll say summary of model 2, model 1. Right, this gives me the overall summary of the model. So once we got it, so what is that it's saying? Evaluate the model fit statistics. Initially look at the R squared. The R squared of this model is 55.86%. Right? So which is clearly saying 55.86 percentage of the variation, right? 55.86 percentage of the variation that is present in the overall satisfaction is typically being explained by these 4 variables that you have typically considered, which means the remaining 44.14% of the variation of the overall satisfaction is not explained by these 4. There is a possibility that it might be explained by something else, or it might be completely random in nature. So that's the kind of interpretation that I can bring out by using the R square. Right, I can simply say 55.86 percentage of the total variation that is present in my dependent variable is explained by the independent variables. So the remaining portion of the variation is not taken care by my predictor variable. So either some other variables got omitted, or I can say that that much of randomness is present as a part of my estimate, as a part of my model. So that's one thing that we are looking at. Then we are also looking at the residual standard error. Here it is 10.59. So whatever I am trying to predict, on an average I can expect the standard error of the model is around 10.59. So that much of randomness, that much of error will be there as a part of our estimate that we are creating. So the lesser the value, The higher is the predictability of the model, the higher the value, the lower will be the predictability. So I have to really see what would be the typical, how to what extent I can bring this down. So with this kind of an exercise, I am able to get the residual standard error to 10.59. And generally, as a quick ballpark estimate, if I am predicting some value as X, we say that the 95% confidence interval of our prediction is X plus or minus then 1.96 times the standard error, which is nothing but the 95% confidence interval value assuming the normality of a distribution. Then the third thing that I am checking is the symmetric nature of the residuals. And the symmetric nature of the residuals can very well be looked at from the first quartile and the third quartile in the data. Right? If they are more or less looking like symmetric on either side of the mean or the median, if they are looking pretty much from the median, if you see median is 1.0, so I can look at either side of the median. If the distance is more or less similar, I can very well say that the residuals are more or less symmetric. So all these things I can very well look at and try to get the first feel of the model. And I can very well do the plot. So I can do a plotting of the residuals just to see that there are no patterns in the residuals which are indicating the non-linearity. Let's look at the plot of model 1. Okay, it would have been better if we had made it into 4. Okay, this is a normal plot, normal QQ plot. We have talked about it. So there are a few variables, a few records which are slightly away from this 45-degree line. So some of the residuals are not looking on the normal line. So some of the residuals are away from normal, and you could see some of them are numbered. The numbered ones are typically identified as outliers for us. Right, and you could also see here the standardized residuals wise, you could see more or less distributed kind of a pattern. So there is no conical or some such kind of a pattern. So there is no evidence of non-linearity being present in this data. Even when you look at the residuals versus the leverage, right, more or less everything is towards the left, means the leverage is much on the lesser side to majority of them. No one single component, no one single point is acting pretty dominant, whereas on few of them you could see that, right, item number 59, the record number 475, 441, they have been highlighted as outliers because for them the leverage looks much higher, which when I say leverage is much higher, there is a good chance that when I remove those particular values, they may have a very undue influence on the coefficient. They have a very big change on the coefficients, so their leverage is much higher. The extent to which they are contributing to the coefficient is much higher. So probably it's better that I really look at these kind of variables, these kind of records, examine them before I really go ahead in terms of removing them. So there are not too many patterns in the residuals, right? Not too much of non-linearity observed. One or two outliers are typically seen, but yes, if we want to remove them, we can remove and redo the model and see what is the level of goodness that is typically coming out. Then, once we have done this initial evaluation, then I am looking at the model coefficients. So model coefficients wise, I could see here for the rights, this is the coefficient, but the p-value is less than 0.05. For games, this is the coefficient, p-value is 0.026, which is less than 0.05. Similarly, for the waiting times, also the coefficient is less than 0.05 p-value. And regarding the cleanliness, also the estimate is 0.98, but the p-value is also again less than 0.05. So for all the four coefficients, which are talking about the relationship between the independent variables and the dependent variables. So the strength of the relationship is pretty much good enough, right? So between the overall satisfaction and each of the independent variables related satisfaction, which are the predictor variables, so all of them I could see they have p-values less than 0.05. And when I look at the coefficient numbers, these numbers, they are a measure of the strength of the relationship, right? How strong is the relationship between the variables? And as long as the p-value is less than 0.05, I can say that the relationship, the contribution of the variable to the overall dependent variable is significant enough statistically. So I'm checking for the p-values for each of the predictors. If it is less than 0.05, I say all those predictors are pretty much significant. And if required, I can very well go with the coefficient plot, which we have done earlier as well, which is there as a part of the coef plot package, where I can visualize the coefficients to really see what is the level of confidence, that is what is the confidence level of each of these coefficients. So is there a possibility of any of these coefficient values going to zeros? So I'll install the package accordingly. Coef plot package is what I will install to have a kind of a plot of the coefficients, right? Along with the 95% confidence interval for the coefficients, I can try to have a plot. So I'll use this coef plot package, and I have a coef plot as a function. So I'll load this coef plot package, so which is to do with the coefficients plotting. Now this particular function coef plot, it actually takes care of the model. So I'll plot the model 1. So in the model 1 I really don't need the intercept term, right? So that's where I set intercept to be false, which means it will plot only the coefficient. And I can also set the confidence interval by using this outer CI. Outer CI is 1.96, which says that I'm going with plus or minus 1.96 times the standard error as the definition of the confidence interval. So 95, because I want a 95% confidence interval, I'll set it to 1.96. Now based on this, I would like to go with a coefficient plot. This is how the plot is going to come. So I could see here regarding the cleanliness, the 95% interval is the coefficient for the cleanliness, it is somewhere from here to here. For waiting time, this is the confidence interval 95%. For games, this appears to be the 95% confidence interval, and for rides, this appears to be the 95% confidence interval. So there is a slight possibility of the games coming very close to zero, but still it is not. So games is also significant. whereas the other three are much comfortably significant. So even this kind of mechanism clearly tells me which variables are impacting my dependent variable quite heavily. Right, I could see that the satisfaction with respect to cleanliness is impacting the overall satisfaction much heavily, whereas the satisfaction with respect to the games is not that heavily influencing the overall satisfaction. So this is one more kind of analysis that I can get into by looking at this. So once I have plotted this coef plot, I can even sort the plot so that the coefficients are in order based on their estimated coefficient. So I can very well sort based on their estimated coefficient values. I can typically sort that, and finally I can quickly identify the features that are most closely related. So here also I could see that this is the order in which they are present. So the graph is very clearly telling me that cleanliness is the most important factor that is being considered as a part of the driver of overall satisfaction, whereas the satisfaction with respect to the games is looking much on the lower side. Alright, let's move to the next one. Now here I would be interested in comparing the models. So when I want to compare two models, one is I'll compare their R squared values. So the higher is the R squared, the higher is the predictability that is associated with the model. So whatever the summary I am doing, within that summary, if I say $R squared, I am going to get the R squared value. So if I say model 1, so I have to take the summary of model 1 $R dot squared. So it gives me 0.558621. So that's the kind of R squared I am going to get. Let's say let me use another model, right, which contained the simple linear regression model. So let me use this, let me call this as model underscore simple linear regression. So I'll take only the games here, I'll not take the other thing because it's a simple linear regression. Overall satisfaction I'll take only with respect to the games. So this is the model I got. Now for this particular model underscore SLR, I can very well go with the R squared. So I'll go with summary model underscore SLR $R squared. Now this is giving me only 0.19. So the R squared of the multiple regression model is much higher compared to the R squared of the simple regression model. So that's one way I can select. But at the same time, what we are simply saying is a model which is having more number of predictors generally has a very high R squared value compared to the model having just few predictors, and that too in the nested model. Let's say if A and B are the predictors of model 1 and A, B, C are the predictors of model 2, what we are simply saying is this model will have a much higher, or at least a marginal R squared higher compared to this model in any case. So the R squared of the model which is having a higher number of predictors and is definitely a nested kind of a model, right? One is a subset of the other in terms of predictors. The one that is a superset model will have a higher R squared compared to the other one. So even though that extra variable contributes or does not contribute, I see that the R squared value will be higher itself, which means to evaluate these two models more than the R squared, I need to have a slightly different kind of an indicator, and that is where we are looking at the adjusted R squared between the two models. So the same thing, instead of taking the R squared, we will take the adj dot r squared, which is the adjusted r squared. So the adjusted r squared is actually simply a formula, right, which is just adjusting for number of predictors. It is controlling for the number of predictors in the model. It comes out as 1 minus of 1 minus r squared multiplied by n minus 1 divided by n minus k minus 1. N is your total sample size and k is the number of predictors that you are having as a part of your model. So instead of comparing the r squared between the models, we actually compare for adjusted r squared, and whichever is of the two models is having a highest adjusted r squared, I can very well go with the choice of that specific model. So for model SLR it is 18.97%, whereas for model 1, which is a multiple regression model, it is 55.5. So I could see that even from the adjusted R squared perspective, the multiple regression model is having a much higher adjusted R squared value. So I can still say that the model 1, which is a multiple regression model, is more appropriate model in this particular regard. So that's one more way, right? And then the other way is I can use the ANOVA tables. I can give both the models, ANOVA, model 1, or probably I'll call first model SLR, model underscore SLR, and model 1. I'll do an ANOVA of these two. So the null hypothesis in this ANOVA is both the models are equal. Model 1 is similar to model 2. That's the null hypothesis. The alternate says no, they are not similar. One model is much different from the other. So the p-value is less than 0.05. 2.2 into 10 to the power of minus 16. So it is less than 0.05. So if the p-value is less than 0.05, I'll go with the alternate hypothesis. The alternate hypothesis is no, these two models are not similar. They are typically different, right? So from there I am going to look at the values, and based on which I am able to say that model 2 is much better compared to the model 1, because I could see here the residual sum of squares is 101736, whereas it's hardly 55,000 here. So the error is much lesser in case of the second. So I could say that the second model is much more preferred compared to that of the first model, right? So this is how we can really get into the comparisons of the models. Either I can look at their R squared or the adjusted R squared, or in some cases I can even go for ANOVA as a comparison between the models. Now, the next step that we are looking at here is, now once the model is in place, let's say that model 1 is a model that I am going to go forward with. So that's the model that I have in place. Now I have to use that model to make prediction. So it's as good as saying now I have this equation in place, right, where what is my model 1? So my equation is minus 131.4. So overall satisfaction is equal to minus 131.4, right? I'm just taking it to one decimal, plus 0.53529, so 53, 0.53 times the satisfaction that they have given with respect to rights, plus 0.15 times the satisfaction that they have given with respect to games, plus 0.55 times the satisfaction that they have given with respect to waiting, and 0.98 times the satisfaction that they have given to cleanliness. Now this is what would be the kind of an estimate that I can typically go with. when I am talking of the overall satisfaction that they are carrying with the model. So that is one thing that I can typically look at. So I can take matrix operations wherein I'll take the coefficients of the model and I multiply them with the values, whatever are the ratings that people have given, and based on that I can typically get what is the overall satisfaction that they are going to get. Right, they can get the intercept, so all the coefficients, they can do a multiplication with whatever the ratings that they have given. So let's say I can take the numbers. So let me try out, let's say a person. So first let me take the coefficients. So the way I can take my coefficients is summary of model 1 dollar coefficients. If I look at, so I'm going to get, these are the coefficients, right? So I can take these coefficients, I can do a matrix multiplication. So I'll take up a matrix multiplication with the typical values which a person is giving. So and if I take coef of model 1, even then if I take only coef, then I'll get only these 5 values in a matrix form. But if I say dollar coefficients, I'll get all this. So I can go directly with the coefs. So this is what I'm going to get. So these coefs I can multiply, I can do a matrix multiplication with the ratings that people have given. So I'll do a percentage star percentage. This is what is coming out as a matrix multiplication for me. So I'll do it with C. Let's say they have given 80 for all of them. Right? For all, a person has given 80 as the rating. Then I could see that his overall rating is going to be 46.18 only. As per this model, if he has given 80 towards all 4 of them, it looks like his rating is going to be only 46.18. Right? And I can also use the predict. The other way I can do this kind of an estimate is predict function, where I'll give the object and I'll give a new data. New data is a data frame, same column names as the data that we have used to estimate the model. So it should be the similar kind of a data, right? The data frame. So within that original data itself, probably for the same values, if I want to do a predict, right? So I'll say my model is model 1, new data is equal to survey, and on that survey, let's say let me take 1 to 10 rows or 1 to 20 rows and all the columns. So I'm simply taking survey data using the model 1. So based on this, I will get my model. So it says for the first one, this is going to be the satisfaction. For the second person, this is going to be the satisfaction. So I can get the values here. The same way I can use either the predict or I can even get the fitted. Fitted is I am getting my fitted values altogether. So I'll get the fitted values of the model 1. I can get 1 to 20 even for them. I should get the same result. Right, even here these are the fitted values based on our model. Either I can get them as fitted if I am looking for the existing data itself, the model fitment to the existing data, and if I am looking at the actual, if I am directly using the predict function, I can get it in this way. Both of them will lead me to the same result, especially when the data is the already existing data. So this is one more aspect that we really need to be comfortable with, right? Then, moving to the next aspect, in some cases, there is a need to standardize the predictors, especially if the variables are having different scales. So some of them are the values are 825, 828, 926, 742 in some high 100, whereas another variable is having 0.523, 0.674, some such kind of numbers. So the size and the scale of the variables is pretty much different. So I cannot compare the coefficient values in that case. If the scales are pretty much different, I cannot say that this variable is influencing highest, this variable is influencing the lowest, right? Because the base for both the variables is not the same. So if my objective is to actually do a simple prediction, I really don't need to bother too much about the standardization of the predictors. But if my objective is to influence or to identify which variable is having the highest influence on the dependent variable, right? Which predictor is influencing the dependent variable to the highest. In that case, it is very much necessary that I have to standardize the predictors. So, especially when my job is to compare the variables, so that is very much possible only when I am standardizing the data. It's a common scale. So when I do this kind of a standardization, generally what happens is every observation, the mean is subtracted from every observation, and that entire thing is divided by the standard deviation of that particular data. So that way what happens is every observation comes into a common kind of a scale. So the mean of every row will be more or less 0, and whatever is the number, it is relative distance from the mean in terms of standard deviation. Either it is 1.23 standard deviations above 0 or 1.45 standard deviation below the mean, some such kind of adjustment. And scale is a function which standardizes the numerical variables altogether. So in the same example, let me create a model 3 by just doing a scale, right? So let me take the predictors now, right? I'll create a model 3 or model 2. Let me call it model 2. The only difference being, right, in the model 2 that I have, let me take the model, let me call it model 2, wherein I am taking, instead of overall, I'll take the scale of overall. Means I'm doing the scaling of the overall value. I'm also doing the scaling of each of the variables separately. So I'm doing the scaling of rights. Remember, the scaling will be done only for quantitative variables, not for categorical variables. So I am performing the scale of each of those variables. Instead of maintaining that in the data as additional columns, I'm doing it here itself. So if you want to really maintain that as a part of the data, you can still do that, right? So this is what I'm trying to go with as a model 2. So a model 2 got built. So let's see how the model 2 is. I'll take the summary of model 2. So this time it is coming out that the R squared is not changing. Though I have changed all these things, my R squared is still 55.86. Adjusted R squared is still the same. Right, the p value is still less than 0.05, saying the model is very much significant. And probably you look at the each of the independent variables, even they are looking, the p values for each of the independent variables is still the same, which means none of these things are changing when I have gone for a scaling. But the difference is pretty much important that we have to look at these coefficients now. Now these coefficients, if I try plotting this coefficients, right, let me go with coefplot, wherein now I'll give model 2 as the input for my coefplot, right. I don't want the intercept, so I'll set intercept equal to false, and I can put outer confidence interval as 1.96. This is a perfect way of talking of which variables are influencing to what extent. So this is a clear-cut mechanism. Small difference you could see now here. The satisfaction with respect to the waiting times is looking more and more significant compared to the cleanliness. Earlier it was seen that the cleanliness was given the highest weightage, but now there is a slight difference in the overall allocations. I could clearly see that the kind of satisfaction level that they are giving to the waiting times is having a much bigger influence on the overall satisfaction levels compared to the satisfaction that they are having with respect to the cleanliness. Well, but overall it is looking like for games it is still on the lower side. So whether you want to standardize it or you don't want to standardize it, it purely depends on what is the kind of use you are having with respect to this particular model. If my objective is more and more of doing a prediction for some new set of data, I really don't need to bother about the standardization or the scaling part. But if I really want to identify what are the drivers which are influencing my dependent variable and what is the order in which each of the variables are influencing the dependent variable, I am more concerned regarding the relative contribution, not the absolute values. So wherever the relative positioning, relative contribution of each of the variables to the overall needs to be looked at, it's better that I do a standardization so that I get the much better responses out of the model. So if the outcomes and predictors are all standardized, we will see that their mean will be 0. That is what we could see here. The mean is 0, the intercept is 0. So that's a straightforward step. So intercept will be 0. Now that is what I got here. Minus 2.8 into 10 to the power of minus 16, which is very close to 0. But I cannot remove it from the model because I will get that value when it is being used as an input, but I cannot remove it from the model and I cannot typically execute only with the other 4 predictors. So that's one more thing that we really need to understand here. So standardizing the predictors is also one more important aspect as a part of our modeling process, right? Then the next part is when I have to look at how do I add factors as my predictors. So I want to try, we have a few factors in our model, right? Whether they want to visit something on a weekend or not, whether they have visited the park on a weekend or not, that's a kind of a factor variable, right? And probably I can very well think of number of children, right, which they had. Even this I can treat it as a factor variable. So I want to add these two things as a part of my factor variables to really try to understand if my model can very well be improved. Now what happens when I provide these factor variables as input into my LM model is automatically, if they are factors, R will convert them into an equivalent. It will assign a kind of a numerical value which is called as a dummy variable, and based on that dummy variable allocation, the meaning of the dummy variable is, so let's say I have number of children as 0, 1, 2, 3, 4, 5. Now it will create variables saying children 0. So this is one variable, children 1, children 2, children 3, children 4. These are all different variables now. And depending on whether for that particular observation it is one child, zero child or not. If it is zero child, then it would be put as 1, and if it is not zero child, it would all be put as zeros. Similarly, if that particular data has one child, there it will be putting as 1, all others will be put as 0. So the data will be modified with this kind of a setup for every factor variable, right? So R actually does this automatically. We don't need to bother more about it. So I have to really give the input as the factors. When I give the input, all the factor variables as input, it automatically does this kind of a process. So in the LM function that we are using for linear regression model, we can use both the numeric variables and the factor variables as the overall predictors of the model. So we can very well convert them into if at all something is a numeric, right, but I really want to use it as a factor, better I can convert it into a factor and I can typically use it, right? I should convert it into a factor and then I can use it as a part of my model. So you can really look at this. We'll create one more model now. Let me call it as model 3, wherein I'll use the LM. I'll take overall as my dependent variable. My independent variable is still the games, rides, waiting time, cleanliness, but I'll give the factor that I have is weekend, and I also have number of children, but that's taken as a number. So what I'll do is I'll have it as a factor. So that's where I'll put factor of num child. Right, I'll put it as factor of num child, and this is where I'll set data equal to survey. So I am taking all these as my variables. Now this is where my model 3 comes out. Let me look at my summary of model 3 here. So here you could see that there are a lot of things that are coming out. So the factors it creates, now we have children as 0, 1, 2, 3, 4, 5, right? So there are 6 different categories. What R does is, out of 6, it takes 5 of them and it creates 5 different variables, which is nothing but n minus 1. So it has created child 1, child 2, child 3, child 4, child 5. So these 5 are created as 5 different variables. And 0 will be taken as the base. Right? So it is like this. So if the child 1, so wherever child 1 is 1, wherever the child is only one child, this variable will have a 1, and wherever it is not one child, it will have 0. Similarly, wherever the particular data has 2 children, there this variable will be set to 1, all others will be 0. Wherever there are 3 children, that particular element will be set to 1, all others will be 0. Similarly in case of 4, similarly in case of 5. But when you look at if there are 0, all these will be set to 0. Now that is why I am calling the 0 children scenario is a base, and all others will be in relativeness with this particular base. So that is what I am trying to look at. Interpret each coefficient for this predictor variable as a difference between the level of the factor and the baseline level. So baseline level, I always look at it with respect to intercept. And with respect to this intercept, I'll look at, okay, if there is one child, it is 16, the satisfaction is 16 more than the base. Whereas if there is 2 children also, the satisfaction is 16 more than the base. Even if there is 3 children, even it is 15 more than the base, and so on. So more or less all these are 16, 16, 15, 14 kind of thing more than the base. And now if in this whole thing, if I am looking at the p-value for this one is less than 0.05, is greater than 0.05. Now in this setup, I can see that the games are not influencing the overall satisfaction, and even the weekend S. This is the variable because weekend has two categories, yes and no. So one of them will be taken as a dependent variable and the other one of them will be taken as a variable and the other one is taken as a part of the base itself. So weekend yes is also having a p-value greater than 0.05. So which means weekend is not influencing the dependent variable at all. And similarly, the satisfaction level with respect to games is not influencing the overall satisfaction. But yes, the number of children that are visiting, they are able to influence the overall satisfaction. So compared to the people who are visiting with no children, the overall satisfaction is higher even if one child is there, two children are there, and up to 5 children. But there's not too much of a difference between one child versus two child or three child, four child. But at least there is a significant difference with respect to no children visiting the park. So for people where no children are visiting the park versus the people where at least one child is visiting the park, I could see that the significance levels are higher. So at least we can make a conclusion that people who are visiting the park with at least one child, their overall satisfaction is much higher, all else remaining the same compared to the people who are visiting the park without a child. Right? So that's one thing that we are able to bring out. And overall now if you look at the R squared, now it has become 77%, which is a big improvement. Even the adjusted R squared became 76.95%. So now if I want to go ahead and typically do the prediction, this would be a much more appropriate model. You could look at the residual standard error now. It's only 7.633, whereas earlier it was in the range of 10.59. So we were able to improvise the model. We were able to reduce the residual error. We were able to we were able to increase the R squared and the adjusted R squared. That is where there is a good level of improvisation that we are able to do with respect to this particular model. So that's one kind of an improvement, right? So now the next aspect that I can look at is how do I really bring in the interaction terms. So when we are talking of interaction between two variables, I can use this colon operator between the variables. So when we talked about variable 1 and variable 2 influencing my dependent variable separately, we have given a plus operator. But if I want to know the interaction, how V1 and V2 together are influencing the dependent variable, then I'll use a colon operator. Instead of these three separately, I can think of V1 star V2, which will take V1 plus V2 as well as the interaction between V1 and V2. So even that can be typically done. And we can look at the kind of interaction between the various variables and to see if the R squared of the model can be improved by any chance because of this interaction. And whichever the interactions are not significant, we can very well think of dropping those non-significant kind of interactions. So if the same example, now let's say I want to build model 4 where I want to build in the interactions between all the pets. So I'll use the same LM overall and this time I go with rides, games, weight, clean, and probably I would also look at weekend. I will not have it, or let me put in even weekend and even the factor of num dot child. But this time I can put in a couple of other interactions as well. Even this, right, instead of putting all pluses, I can even think of putting all stars. Instead of all pluses, let me think of putting all stars. But if so many variables are there, I put stars, it might get too much of difficulty in terms of executing, because all the pairwise interactions would typically be looked at and evaluated by the model. Okay, I have to get the data name, right? So let me get data equal to survey. Okay, so this is what has come out. So let me take a look at the model 4, what has come out. And because it starts, I get so many variables coming out. Right, all these variables are typically being brought in. So if I look at this, estimate standard error for all these variables, now I can clearly see initially rides, games, weight, clean, weekend, yes, factors, all are there. Now two variable interactions, rides and games, rides and weight, games and weight, rides and clean, games and clean. So I get all these two variables kind of interactions. Now they have moved to three variable interactions. Again, there are three variable interactions, all these things. So we could see that it keeps going on and on. Now you have four variable interactions here. So like that, all the pairs typically come into picture, right? But now look at the significance levels. The R squared might have gone to 87. Adjusted R squared is 79.9. But if you look at the significance levels, yes, look at the significance levels here. Which of the ones are less than 0.05? It looks at one, this one, 0.08. This is not less than 0.05, less than 0.0, less than 0.1. The same is going with weight, weekends, and when there are two children. Then similarly, games, rides, games, weekend with two children, some level of thing, and similarly, rides, weekend with two children. So these were the variables that were influencing, but none others, neither the rides nor the games. So this is where somewhere theoretically, I mean, if I give something like this, statistically I am getting some kind of a result, but theoretically there is, no, I cannot really make any kind of an implication. So we have to be very careful about the implications. I need to just really think what kind of interaction terms really make some kind of a sense, and only those interaction terms need to be included or incorporated as a part of the model. So we have to understand that the model, whatever we are building, it is focusing on the association but not the causation. So I would standardize the predictors when modeling the interactions so that I get interpretable and comparable scale for the coefficient. So especially when I am bringing in the interaction terms into the model, I would always prefer having some level of scaling or standardization of the variables rather than taking the variables as they are. So that's one more place where I can really look at standardizing the variables. So whenever I am including the interaction effect, make sure that the main effects are also included. So either you use them as x star y or at least use it as x plus y plus x colon y. So that's what we need to be comfortable with respect to the interaction terms. Now, when you have to really look at the interaction terms in the model formulas, these are the typical ways of including them. Right? These are the different kinds of syntaxes we are talking of when we are handling the interaction terms as a part of our model formula. When I simply put y tilde x, then it's like I'm trying to model the relationship between y and x. Y is a linear function of x. But if I put it as x minus 1, it means I don't want the intercept term. I want to go only with the x term. If I put y tilde x plus z, then I am looking at linear combinations of x and z. X and z are the predictor variables which are trying to predict the dependent variable here. Then x colon z means we are including the interaction between x and z. X plus z is not included here. Then when we are talking of x star z, we are talking of both the things, x and z, the main effects, as well as the interaction between them. Then if I say u plus v plus w, and if I raise it to the power of 3, it means up to 3 interactions, everything will be taken. U, v, w, their main effects, then uv, uw, vw, their interaction effect, and even uvw, which is a three-way interaction effect. All are being considered when we are saying u plus v plus w raised to the power 3. But if I put u plus v plus w raised to the power 3 minus uv, then I am not looking at the uv interaction term, but all other interactions I am typically looking at. So these are the different ways in which I can include different kinds of interaction terms as a part of my model formula. Then one area that we need to be slightly careful of in this context is the overfitting. The more and the more predictors I am trying to add to a model, whether it is the main effects or even the interaction effects, one-way, two-way, three-way, four-way interaction effects, the more and the more predictors I am trying to add to a model, the estimates of the coefficients, they get very diluted. So the precise nature of the coefficients will typically go off. So the number of effects will typically increase, associations increase, but the precision gradually keeps going down. And if the coefficients are if the precision of the coefficients is very small, then probably I cannot use the model for my business purpose. And this is where we say the model is getting overfit. I cannot really create some business utility out of that model. And it can finally lead to me making wrong conclusions, wrong inferences regarding the relationships between the variables in my data. So when we are talking of looking at the model, I should very clearly look at the standard error of the coefficients. I should really have much smaller standard errors, which means the precision of the coefficients would be much better. So I should see that the coefficients will have very small standard errors so that they become more and more reliable estimates rather than a big increase in the standard error of the coefficient. So in some cases we even suggest to take some subset of the data, call it as a training data, develop the model using the training data, and some subset of the data take it as a test data. Whatever the model that we have developed, test it on this data, and if the results are more or less similar, then you can go ahead in terms of using the model for the real world implementation. In that case, you can see that because you have tested it out on the testing data also, the reliability of the model is much better. So you have to really use the predict and use this model to predict the test term for which you already have the dependent variable, compare the predicted values that your model has given versus the actual values that are present for this test data, so that the overall overstepping can be eliminated altogether. Or there is another mechanism which talks about the step. So if you typically do this, right, I could simply call, let's say, model 5. I'll use a step function, right, wherein I'm talking of the linear model of overall until I'll put a dot saying all other variables, right, and the data that I'm looking at here is the survey data. Alright, I really need not put the bracket here. I need it overall, and then we are taking data equal to survey, and I'm closing it here. Now if you see this is the overall model. It is going step by step, right? Initially all the variables are being included. So based on that, it has taken the AIC. So AIC is the KK information criteria. So where if it has removed the weekend, this is the AIC. Removed nothing, it is this AIC. Removed each of these, the AIC is going up, which means only the weekend can be removed. So the weekend is removed, and this is what is going to be the model. Number of children, so overall is being looked at as number of children, distance, rides, games, weight, and clean. So the AIC now, any of the variables removed, the AIC is increasing, which means I cannot remove any of the variables. So this would be my typical model, right? I would go ahead using this. So I can take the summary of this model 5. So the summary of this model 5 typically goes with this, wherein the R squared is 68%, adjusted R squared is 67%. So this is also one more way where I can look at a step-by-step usage, and based on which it can remove the variables or it can add the variables accordingly, and the overfitting can be eliminated in a much better manner by doing this stepwise exercise. So just to summarize, if at all I have to get into a complete linear model fitting, these are the steps which we have done till now. I'm just quickly summarizing them. First, inspect the data. Make sure it is clean. No NAs are there in the data. Look at the structure. Make sure that all the variables which you want them to be factors, they are factors. Which you want them to be numbers, they are numbers. So look at the types of each of the variables. Look at the distribution. See that they are not highly skewed. If they are skewed, consider some kind of transformations like logarithmic transformation, square root transformation, etc. Or even a box-Cox kind of a transformation. So create some kind of transformation if the data is highly skewed. Then look at pairwise relationships, bivariate scatter plots. Wherever required, go with a correlation matrix. See the level of correlations that are existing between the variables. If they are very strongly correlated, if the predictor variables that we are talking of, they are very strongly correlated, see that some of them can be omitted, or if required, someone can be transformed as well. So that one exercise you can typically do. Now, when you are really looking at estimating the coefficients, where the scale need to be consistent, where my objective is to compare the various coefficients and say which variables have strongest influence on the dependent variable, then you use the scale function, typically standardize those variables. Then once your model is fitted, look at the residual quantities. So look at if they are very much symmetric or not, Q1 versus Q3, and see how much the model is accounting for the individual observation. What is the residual value, the extreme residual values, to what extent the minimum error is and the maximum error is. And otherwise, look out for standard model plots. We talked about the 4 plots, which are generally plotted for any kind of regression model, wherein the residuals, right, the 4 graphs that we talk of, residuals are plotted against the fitted values. Square root of the standardized residuals are fitted against are plotted against the fitted values. Then QQ plot, normal QQ plots are typically plotted to check whether the variables are, whether the residuals are pretty much normal in nature, or there are some variables which are pretty much extreme, which can be identified as outliers. And the 4th graph that would be plotted is primarily between the leverage and the square root of standardized residuals to simply check to what extent a particular point is influencing your dependent variable, your coefficients. So all these things you can plot, and you can also check whether the linear model is more and more appropriate to the data that you are fitting, or there is present some level of non-linearity in the model. And you can also even identify the potential outliers in the data, and if possible try to omit them. So try different kinds of models, compare them, do the model fitting, look at the residuals, check the overall R squared, check the residual standard error, and based on them choose the model which is more and more fitting to the data more appropriately. And once the data is fitted, you can very well report the confidence intervals of the estimate along with the coefficient, make your recommendations and interpretations accordingly. So this is the kind of summarized procedure if you are more and more looking at going ahead with linear model fitting exercise. So this is what I wanted to cover as a part of this session. So all these things we have looked at in more and more depth. If you have any further queries regarding the same, you can very well get in touch with me by giving me a call on the number that I have provided below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.